This video is going to cover section 4.6, differentiability. A function is differentiable if it has a derivative. And so there are three ways a function can fail to be differentiable. And back when we were graphing functions and their derivatives, there was a worksheet where there were times when if the function had a couple things going on, the derivative graph would have an open circle. And so one of the first things that we talked about was when a graph has a cusp or a sharp point. And so if you think about the derivative from the left and the right side of a cusp, it's approaching two different values. And so the limits of all the average rates of change from the left and the right aren't approaching one number. And so you can't have a derivative if the left side has a derivative of 10 and the right side has a derivative of -3. It's not approaching the same value. So when a function has a cusp, you will not have a derivative at that point. And so in the graph of the derivative, you would have an open circle. Another way that a function can fail to be differentiable or have a derivative is if that function is discontinuous at that point. So whether it's a removable discontinuity, a jump, or an infinite discontinuity, you can't have a derivative at a point that doesn't exist or jumps from one value to another. And lastly, the vertical tangent line. So we had a graph of a semicircle once, and when we were getting closer and closer to the left of that semicircle, the slopes were getting steeper and steeper, and a vertical tangent line has an undefined slope. And so because I can't give that value a number, or that slope a number, I can't have a value on the derivative function's graph. And so when a function has a vertical tangent line, you won't be able to have a derivative at that point. So the definition of differentiability or having a derivative at a point is, first of all, that derivative exists. And then second of all, if we're talking about an interval or on a function, it has to be differentiable on an open interval. And so that means it cannot include the endpoints. And so that's why parentheses and brackets, it's really important to know the difference. We can be continuous at an endpoint, so continuity can have closed brackets, but differentiability has to be parentheses. And the reason is because the slope at a point, we have to know what the slope is on each side of that point. And so if we have a graph that stops at x equals 4, and there's nothing to the right of 4, I don't know what the slope would be as I approach 4 from the right. And so it has to be an open interval. We need to know what's going on both sides of a point in order for it to have a derivative. And then there's the theorem. It's if f is differentiable at c, then you know f is continuous at c. And so from now on, if I say that a function is differentiable, then you should already know that it is continuous. But not all continuous functions are differentiable. So that's like having a cusp. So the steps to determining if a function is differentiable at a point is the first thing you have to know if it's continuous. And so that means going through the 3 steps of continuity. So does it have a y value? Does it have a limit? And does the y value equal the limit? The next thing is that you would need to find f prime of x's equation. And then after that, you are going to use one-sided limits to determine if f is differentiable at x equals c, meaning the left limit of c on the derivative and the right limit approaching c of the derivative are equal. If the limits are not equal, then that means f has a cusp and it's not differentiable. So my first example is f of x. Here's this piecewise function. Part of it is a quadratic, part of it is a line. So first thing is checking continuity. So I'm going to plug 1 into the top equation because that's where x is less than or equal to 1. When I plug 1 in, I get 6, so it has a y value, it exists. Checking the limit from the left would be using that same equation, and I get 6. Checking the limit from the right, when I plug in 1, it would be the bottom equation, and I get 6 minus 5, which equals 1. The limit does not exist because the left limit and the right limit are not equal. And so that means f of x is discontinuous at x equals 1, therefore it is not differentiable at x equals 1. So you don't even need to go forward to find f prime. My second example is another piecewise function. This is made up of two quadratic equations. So the first thing is finding f of x, and I'm using x equals 1. I will tell you what the c value is, but in this case, because the piecewise functions are broken up at 1, that's my c value. So when I plug 1 into the bottom equation, I get 1 squared, but then make it negative. So just make sure with this one you're following order of operations and you're not squaring a -1. So -1 plus 4 is 3, 3 minus 1 is 2. So it has a y value. The limit from the left, I'll be using the top equation now. 1 squared plus 1 is 2. The right limit is the same thing as what I used for the y value. So the limit is 2, the y value and the limit are equal. So right now we know it's continuous. So now we need to go on and find f prime of x. So finding a derivative of a piecewise function is just finding the derivative of each piece. So just power rule, the top part is 2x for x is less than 1, and then the bottom part would be negative 2x plus 4, and that is x is greater than 1. Now notice that the bottom part of the derivative is just x is greater than 1. You can't include an underlined or a less than or equal to or a greater than or equal to, because this could be an endpoint and we can't have a derivative at an endpoint. So when you find f prime of x, always take out the less than or the greater than or equal to part. So now finding the left limit of the derivative as x approaches 1, I'm going to get 2. I'm using the top equation. Checking the limit from the right, I'll be using the bottom equation. I also get 2, and so therefore the limit as x approaches 1 of f prime of x is also 2. And so since the limit of the derivative is 2, it is differentiable. And this value is the slope. So it's just a coincidence that when we went to the f of x and I plugged in 1, I got 2. That just means at the point 1, 2, I have a slope of 2. So you won't always get the same limits of f prime as you did with f of x. That's just a coincidence. So what I want you to do is to partner up and to determine if these following functions are differentiable at x equals c. And so I'm giving you c is 3 and c is 6 for number 3 and 4. The substitute has the answers for these two, so you can check your work. And then when you're all done, you are going to be doing a differentiability investigation. So you'll be going through kind of the same steps, but now you're going to be solving for A and B, solving for some unknowns to determine if the function is differentiable at a specific point. And when you're all done, then you'll pick up the homework. You can check your answers with the answer key, and then you can pick up your worksheet. You will just be picking 5 problems to complete. Have a good day. I'll see you tomorrow.